Hey there! I'm really excited to walk you through this research content today. We're going to cover research methodologies, statistical concepts, the research process, validity and reliability, and how to identify different study designs. This might sound dry, but I promise it's actually really practical stuff that you'll use throughout your career. Plus, it's definitely going to show up on your exam. So let's make sure you understand it well enough to nail those questions when they come up. All right, let's talk about what you really need to know for the exam. These 5 concepts are the most commonly tested research topics, so pay special attention. You'll need to know the difference between quantitative and qualitative methodologies. That's a big one. You should also be able to identify study designs and know their strengths. Statistical significance interpretation comes up a lot too. And don't forget about research validity and reliability. Those are huge. Finally, hypothesis types and testing round out the top 5. If you master these areas, you'll be in great shape for the research questions on your exam. Now we're getting into the meat of things with research methodology. This section is super important because it lays the groundwork for everything else. Honestly, if you don't understand the basic approaches to research, the rest won't make much sense. So let's break it down in a way that's easy to grasp. Okay, here's one of the most fundamental distinctions in research: quantitative versus qualitative. Quantitative research uses numbers and statistics. It's all about measurable data. You'll use statistical analysis to test specific hypotheses. Remember for the exam that this is considered the most rigorous evidence, especially randomized controlled trials. On the other hand, qualitative research examines things continuously. It's more about narratives and observations, the stories and experiences that numbers can't capture. It explores meanings rather than measurements and helps develop theories instead of testing them. The exam often tests if you can distinguish between these two approaches, so know the characteristics of each. Here's something you absolutely need to memorize: the evidence hierarchy. Think of it as a pyramid with the strongest evidence at the top. At the very peak are meta-analyses and systematic reviews. These combine results from multiple studies. Next come randomized controlled trials, or RCTs. Then we move down to cohort studies, case control studies, and cross-sectional studies. At the bottom, with the weakest evidence, are case reports and expert opinions. When you're looking at a research question, always consider what level of evidence you're working with. Let's get practical about how to identify study types in exam questions. This is really important because often the question won't directly tell you what kind of study it is. You'll need to figure it out from the description. For RCTs, look for these 3 elements: randomization, control groups, and an intervention. That's your gold standard. For cohort studies, the key is that they follow groups forward in time. Case control studies work backward from an outcome. Cross-sectional studies take place at a single point in time, like a snapshot. And case reports focus on just one patient. Now, for hypothesis questions, which come up a lot, there are 3 main types you need to know. A directional hypothesis states which way the relationship goes, like weight gain increases with garbage feeding. A non-directional hypothesis just says there's some kind of relationship without specifying direction. Weight gain relates to feeding method, and the null hypothesis says no relationship exists. Weight gain is unaffected by feeding method. The exam often asks you to identify which type is being used in a scenario, so make sure you can spot the differences. Moving on to statistical concepts. This section scares a lot of people, but it's really not that bad once you break it down. You don't need to be a math whiz to understand the basics of how statistics work in nursing research. Let's talk about the 2 main categories of statistics. On the left, we have descriptive statistics, which simply summarize the data you've collected. These include things like mean, that's your average, median, the middle value, and mode, the most common value. You'll also see standard deviation, range, and variance, which tell you how spread out your data is. The exam often asks basic definition questions about these. On the right are inferential statistics, which let you make predictions about populations based on your sample. These are used to test hypotheses and determine if your results are significant. The exam tends to focus more on applying these concepts rather than just defining them. So make sure you understand not just what they are, but when and how they're used. Here are some high-yield statistical terms you absolutely need to memorize. First, a p-value less than 0.05 means your result is statistically significant. A type 1 error is a false positive. You think there's an effect when there isn't one. A type 2 error is a false negative. You miss an effect that's actually there. An important distinction: statistical significance doesn't always mean clinical significance. Just because something is statistically significant doesn't mean it matters in real patient care. And remember that the independent variable is the one you manipulate in your study. Speaking of variables, let's clarify the different types. The independent variable is what you manipulate or change in your experiment. Think of it as the cause. The dependent variable is the outcome you measure, the effect. Confounding variables are those pesky influences you didn't control, for that might mess up your results. And control variables are the ones you keep constant throughout the study. The exam loves to test your ability to identify variables in research scenarios. Now we're shifting gears to research utilization. This is where theory meets practice, how we actually use all this research knowledge in our everyday work as NNPs. This connection between research and practice is crucial for providing evidence-based care. The research process follows key stages that you need to know for the exam. It starts with identifying a problem and reviewing relevant literature. Then comes formulating a hypothesis and selecting an appropriate design. After that, you select your sample and collect your data. Next, you analyze and interpret that data. Finally, you disseminate your results. The exam often tests your knowledge of this sequence and the components of each stage. Knowing the logical flow of the research process will help you answer these questions correctly. Let's look closer at hypothesis development. A good hypothesis comes from either theory or observation. It must be testable and measurable. If you can't test it, it's not a scientific hypothesis. It states the relationship between variables and provides direction for your methodology. It also helps determine which statistical approach you'll use. Literature reviews establish what's already known about your topic. You'll need to distinguish between primary sources, original research, and secondary sources, summaries of research. A good review critically evaluates existing research, not just summarizes it. It identifies gaps in current knowledge and provides the foundation for new research. You may see questions about the purpose and components of a proper literature review, so understand what makes one effective. Now we're moving into a critical area: research validity and reliability. This section is about how we know if research results are trustworthy and accurate. Validity is about whether a study actually measures what it claims to measure. Internal validity asks, did the study measure what it intended to? External validity is about generalizability. Can the results apply to other situations or populations? Construct validity concerns whether the concepts were adequately measured. Content validity examines if all aspects of a concept were covered. And face validity is the most basic. Does the instrument appear to measure the concept? Reliability is all about consistency. Test-retest reliability asks if you get consistent results over time. Inter-rater reliability looks at consistency between different evaluators. Internal consistency checks if all items in a test measure the same construct. Parallel forms reliability sees if different versions give the same results. And split-half reliability involves dividing a test to see if both halves yield similar results. You may be asked to identify which type is being described in a scenario. Here's a crucial distinction. Validity is about accuracy, hitting the target, while reliability is about consistency, getting the same results repeatedly. You can have reliability without validity. You might consistently get the wrong answer. But you can't have validity without reliability. Both are essential for quality research. You may be asked to distinguish between these two concepts in various scenarios. Remember the analogy: a broken clock is reliable. It shows the same time consistently, but not valid. The time is wrong. Let's go deeper into study designs. Experimental designs manipulate an independent variable. True experimental designs have random assignment plus a control group. Quasi-experimental designs lack random assignment. Non-experimental designs don't manipulate anything, they just observe. These include descriptive studies that observe and describe, correlational studies that examine relationships, and case studies that provide in-depth analysis of individuals. Experimental designs have several key features: random assignment to conditions, a control group, manipulation of an independent variable, pre-test and post-test measurements, and control of extraneous variables. Random assignment is particularly important. It helps ensure that differences between groups are due to your intervention, not to pre-existing differences. The exam may ask if you can identify true experimental designs versus other types, so look for all these elements. Let's review non-experimental designs. Case control studies work backward from an outcome to find potential causes. Cohort studies start with an exposure and follow participants forward to see what happens. Cross-sectional studies examine everything at one point in time. Correlational studies look at relationships between variables without manipulating anything. And descriptive studies simply observe and document phenomena. You may be given a scenario and ask you to identify which design is being used. Sampling methods fall into two main categories: probability and non-probability. Probability sampling gives everyone in the population an equal chance of being selected. Types include simple random sampling, equal chance for all, stratified sampling, proportional subgroups, and cluster sampling, selecting natural groups. Non-probability sampling doesn't give equal chances. It includes convenience sampling, easily accessible subjects, purposive sampling, deliberately chosen subjects, and snowball sampling, referral chains. Sample quality affects how trustworthy your results are. Sample size impacts statistical power. Generally, bigger is better. Representativeness determines if your sample reflects the population you're studying. Inclusion and exclusion criteria define the boundaries of your sample. Attrition refers to participants dropping out during the study, and response rates affect generalizability. Low response rates may indicate bias. You may be asked to identify problems with samples in research scenarios, so look carefully at how participants were selected and maintained. Sample size is determined through power analysis, which considers several factors. Effect size is one. If you're looking for a small effect, you need a larger sample. Alpha level, typically 0.05, also affects required size. With small samples, you risk type 2 errors, missing effects that actually exist. Adequate sample size is essential for validity. The exam might ask about factors that determine appropriate sample size or problems with studies that have too few participants. We're circling back to statistics now, but we'll dig a bit deeper. This repetition is intentional. Statistics is such an important part of understanding research that it's worth looking at from multiple angles. Let's revisit the distinction between descriptive and inferential statistics. Descriptive statistics summarize your data: mean, median, mode, standard deviation, range, and variance. They paint a picture of what you found. Inferential statistics let you make predictions about populations based on your sample. They help you test hypotheses and determine significance. This basic distinction forms the foundation for understanding more complex statistical concepts. Here are some key statistical tests you should know. The t-test compares two group means, like comparing birth weights between two different treatment groups. ANOVA, analysis of variance, compares three or more group means. Chi-square compares categorical data, like whether treatment A or B resulted in more successful outcomes. Correlation measures relationship strength and direction between variables, and regression predicts values based on others. Let's reinforce some high-yield statistical terms. A p-value less than 0.05 indicates statistical significance. Type 1 error, alpha, is a false positive, while type 2 error, beta, is a false negative. A confidence interval gives you a range where the true value likely lies, and effect size tells you the magnitude of the difference you found. These concepts come up frequently on the exam, especially p-values and the types of errors. Don't just memorize them, understand how they relate to each other in research. One more time with variables because they're so important. The independent variable is what you manipulate. The dependent variable is the outcome you measure. Confounding variables are uncontrolled influences that might affect your results. Control variables are kept constant. And extraneous variables are those that potentially affect the outcome but aren't part of your study focus. Here's a key distinction. Correlation versus causation. Correlation just means two variables are related. When one changes, the other tends to change too. Causation means one variable actually causes the other to change. Correlational studies can show relationships but can't prove causation. You need experimental designs for that. This is a common statistical trap in interpretation that the exam tests just because two things happen together doesn't mean one caused the other. Let me leave you with some practical test-taking strategies for research questions. First, look for key methodological terms in the question stem. They often give away what type of study is being described. Try to identify the study design first when applicable. Watch for distinctions between statistical concepts like significance versus importance. Use the process of elimination for complex questions. Remember that sampling affects generalizability, and be careful to distinguish between validity and reliability. When evaluating research designs for clinical application in neonatal care, which methodology provides the strongest foundation for practice changes? A. Case reports from expert clinicians. B. Randomized controlled trials. C. Retrospective chart reviews. The correct choice is B. Randomized controlled trials. Randomized controlled trials represent one of the highest levels of evidence in research design hierarchy. They use random assignment to intervention or control groups, include control groups, and minimize bias through randomization, providing strong evidence for causality and effectiveness of interventions. Case reports from expert clinicians. Case reports are considered low on the evidence hierarchy because they typically document individual patient experiences, lack controls, and are subject to selection bias. While they may identify new phenomena or generate hypotheses, they don't provide strong evidence for practice changes. Retrospective chart reviews. These are observational studies that analyze existing data, making them subject to selection bias and confounding variables. They lack randomization and controlled conditions, placing them lower in the evidence hierarchy than randomized controlled trials. An NNP researcher is measuring the effect of developmentally supportive positioning on preterm infant stress levels. In this study design, infant positioning represents which type of variable? A. Confounding variable. B. Dependent variable. C. Independent variable. The correct choice is C. Independent variable. The independent variable is the one manipulated by the researcher. In this study, the researcher is manipulating infant positioning, intervention, to observe its effect on stress levels, making positioning the independent variable. Confounding variable. A confounding variable is one that influences both the independent and dependent variables, potentially leading to erroneous conclusions. Positioning is deliberately manipulated in this study, not an uncontrolled influence. Dependent variable, so the dependent variable is the outcome being measured or observed. In this study, stress levels are being measured in response to changes in positioning, making stress the dependent variable, not positioning. A neonatal research team collects data on pain scores, heart rates, and oxygen saturation levels during procedures. When they calculate means and standard deviations of these measurements, they are using A. Correlational analytics, B. Descriptive statistics, C. Inferential statistics. The correct choice is descriptive statistics. Descriptive statistics summarize and organize data through measures of central tendency, like means, and measures of dispersion, like standard deviations. They describe what the data show without making inferences beyond the collected data. Correlational analytics. Correlational analytics examine relationships between variables to determine if and how they are related. Simply calculating means and standard deviations doesn't establish relationships between variables. Inferential statistics. Inferential statistics allow researchers to draw conclusions about populations based on sample data and involve hypothesis testing. Calculating means and standard deviations alone doesn't constitute inferential statistical analysis, which would include tests like t-tests or ANOVA. The implementation of evidence-based practice in the NICU differs from research utilization primarily because evidence-based practice A. combines clinical expertise with research and patient preferences. B. focuses exclusively on randomized controlled trials. C. requires hypothesis testing and data collection. The correct choice is A. combines clinical expertise with research and patient preferences. Evidence-based practice integrates the best available research evidence with clinical expertise and patient family values and preferences. This three-part integration distinguishes it from simple research utilization. Focuses exclusively on randomized controlled trials. This is incorrect because evidence-based practice incorporates evidence from various research designs, not just RCTs. While the hierarchy of evidence places RCTs highly, EBP considers all appropriate evidence sources based on the clinical question, requires hypothesis testing and data collection. This describes the research process, not evidence-based practice. EBP uses existing research findings rather than generating new data through hypothesis testing and data collection. When a tool consistently produces the same results when measuring neonatal pain responses across multiple assessments by different clinicians, this demonstrates the tool's A. Clinical significance, B. Predictive value, C. Reliability. The correct choice is C. Reliability. Reliability refers to the consistency of a measurement tool. Inter-rater reliability specifically refers to the consistency of results when used by different observers, as described in this scenario where different clinicians obtain similar measurements. Clinical significance. Clinical significance refers to whether findings have practical importance in clinical settings, regardless of statistical significance. This concept doesn't address measurement consistency. Predictive value. Predictive value refers to a test's ability to correctly identify a condition or predict an outcome. This is related to validity rather than the consistency of measurements described in the question.